Okay, we're continuing on here, chapter 16, thermodynamics, second part. And in this chapter, we talked about entropy. And again, entropy is delta S, or the change in entropy. And entropy is the amount of disorder or randomness there is. And entropy increases, as we talked about, with the amount of disorder. So the more disorder you have, the greater the entropy. So as the disorder increases, the delta S there becomes again more positive in this case. And obviously, as the disorder decreases, or if you want to think about it more order, whichever way you want to think about it, the delta S there will be negative. We could use something like entropy, as we talked about, to figure out if a reaction is spontaneous or really non-spontaneous. And remember, as we talked about when we were talking about a reaction being spontaneous, it really has nothing to do with, again, how sort of fast or slow the reaction takes place. Spontaneous means in this context that the reaction just should take place. And it could take place under those conditions without any type of outside intervention. And it could take place really fast. It could take place really slow. But when we say something is spontaneous, that's basically what we're saying is under those conditions, that reaction, for example, should occur. And again, it could be fast, could be slow, could be somewhere in between. We could use the delta S of the universe to determine whether or not a reaction is spontaneous, and delta S of the universe is basically equal to the delta S of the system plus the delta S of the surroundings. And again, we calculate each of these things a little bit differently. The delta S of the system are sometimes it's the reaction is referred to. We just do basically our products minus our reactants. So we go to a table, we look up all the delta S's of our products, and we basically subtract it from all the delta S's of our reactants. And that will give us our delta S of the system. Remember that you can make a fairly good prediction of the sign of the delta S of the system based on, for example, gas molecules in an equation. So if you create more gas molecules than you started with, then you cause a lot more disorder because there's a lot more gas molecules flying around. And you would expect the delta S there to be a positive value. Opposite is true if you actually end up with less gas molecules than what you started with, then you're kind of creating a lot more order, if you will, a lot less disorder. Again, I always think about how many things flying around like in your face, there's like 5 things flying around versus like 2 things, so it's a lot more order sort of happening. And the delta S would be a negative number for that. Remember that that value alone will not tell you if the reaction is spontaneous. It's just going to tell you in that reaction, are you kind of increasing or decreasing the disorder? The surroundings, as we talked about, is related to the enthalpy. And remember that the delta S of the surroundings is equal to minus delta H of the reaction divided by the temperature in Kelvin in this case. And remember that negative here is important because it's sort of that opposite relationship that we talked about. As a exothermic reaction gives off the energy to the surroundings, we would expect the surroundings to increase in its entropy or increase in its disorder, as the surroundings would be picking up all that energy, and all the molecules there would then have a lot more energy, a lot more movement and moving around. And we would expect, because delta H is negative for an exothermic process, the two negatives there would then turn your delta S to a positive number for your surroundings, which again would make sense as it's increasing the disorder. Opposite is true if you have an endothermic process. The energy is going to come from the surroundings to the system. The result of that is the surroundings will lose energy, and you can think about everybody in the surroundings kind of slowing down, not as crazy, and again, going to create a little bit more order in the surroundings. And again, with our delta H being endothermic, that would be a positive value for it, and the positive and the negative would turn the delta S for the surroundings negative in that case, which would indicate obviously a decrease in the amount of disorder. Temperature does play a big role in that as well. Again, if you have a really large temperature, as we talked about, may not be a big difference. When you have both of those things together and you add them together to get to your delta S of the universe, if the delta S of the universe is a positive value, then the reaction would be spontaneous. And again, if it's a negative value, then it would be non-spontaneous the way it is written. We then talked about Gibbs Free Energy. Gibbs Free Energy is energy available to really do some type of work, and Gibbs Free Energy is delta G. And one of the things about delta G is we could actually use delta G sort of value or sign of it to directly determine whether or not a reaction is spontaneous or not. So if we calculate the delta G and it is a negative number, then it is going to be a spontaneous reaction the way it is written. If we calculate it and it's a positive value, then it's going to be non-spontaneous. And if delta G actually equals 0, it would actually be at equilibrium at that point. Now, there's a couple different ways here that we saw, I think, up to this point to actually calculate delta G. You can do like all the other thermodynamic sort of properties. You can do the delta G of the reaction by taking the delta G of your products minus the delta G of reactants. Again, you would go to the table, look up the values, obviously use the coefficients like we talked about as well. Another equation that you could use to calculate delta G is one where you have delta H minus T delta S. And in this situation, you would use this equation, obviously, if you had delta H and delta S to solve for delta G. This is definitely one of those equations where, as I mentioned earlier, and a lot of times in this chapter, you do have to be very careful of units to make sure everybody's in the proper units. Once again, delta H is typically in kilojoules and S is typically in joules. So if you just do not do some type of conversion, you will find yourself off, obviously, by that factor of 1,000. So it doesn't necessarily matter which way you convert it, but those guys definitely need to be in the same units. Otherwise, you will get probably the wrong answer in that case. Any questions on any of that stuff there we talked about last time there? All right, then speaking of this sort of equation, as I mentioned, I think the other day, a lot of times you may come across some questions where they really won't give you numbers, but they'll kind of go, hey, this is positive, this is negative. What do you think is going to happen in this reaction? So we could kind of do that with this equation here. So let's take a look at some sort of options. So I'll rewrite this maybe a few times so we can kind of go through the different options here. I'll use that one there. I'll go down this way here. And we'll go over here for this guy. All right, so in this particular case, once again, we got to remember what we just talked about, which is the difference in sort of the units. And remember that, you know, this guy over here is essentially kilojoules, and this guy is in joules. So the first guy there, the delta H, got like 1,000-fold jump almost on the other guy, usually in most cases. So if we have sort of this first box situation here, where we have an endothermic reaction, which means our delta H is going to be a positive number if this guy is going to be a positive number. And we have a increase in entropy, which means that this will be a positive number. We can make a prediction that this reaction would be spontaneous only at high temperatures. And it is the temperature value here that's kind of important, because in order for this back part to sort of overtake the front part, we would need a really large temperature to do that, to make this number larger than this number and turn the delta G into a negative. So when you have that situation of a positive H and a positive S, you would expect a reaction to be spontaneous at high temperatures. It will be really non-spontaneous there at low temperatures because the back part of that formula is not big enough to overtake the front part because it's kind of got a 1,000-fold jump on it to begin with. Now, if we look at, say, this box over here, and that is a exothermic reaction, which means my delta H is going to be negative, and my entropy is still going to increase, which is positive. In this situation, temperature is always going to be a positive number. In this situation, no matter what you do, you will always have a negative number. So you will always hit a negative delta G for that. And that means that the reaction should always be spontaneous, no matter what the temperature is. You will always get a spontaneous reaction. So a negative delta H, a positive delta S would definitely result in a spontaneous reaction regardless of the temperature. If we look at the third sort of box, that is a endothermic delta H, which means that is positive. And we have a decrease in entropy, which means that is negative. This negative, along with this negative, is now going to turn this whole back thing into a positive number. And now you got basically two positive numbers. So no matter what you do at this situation, you're going to hit a positive delta G value. And that's going to mean that this reaction is actually going to be non-spontaneous pretty much at all temperatures because of that. So it really will not proceed spontaneously at any temperature. Lastly here, if we look at sort of our option, we have an exothermic delta H, which is negative. We also have here a negative delta S. That again is going to turn the back part here into a positive value. So at low temperatures in this case, that will prevent the back part of the formula from overtaking the front part. And that will allow you to still maintain a negative delta G at those low temperatures. If you get into high temperatures, that could allow this back part of the formula to basically overtake it and turn delta G into a positive number. So any questions on how to look at those formulas and figure that out there? And again, there are a lot of questions like that in this chapter where they again may just kind of tell you things like that, like this is positive, this is negative. Would you predict it being spontaneous or not? Not really giving you numbers or anything like that. You could also clearly just throw numbers in and kind of do a calculation if you wanted to, but this is kind of what you could look at. Any questions on how to analyze that formula there? All right. So let's take a look at this one here. We have the decomposition of calcium carbonate into calcium oxide and carbon dioxide. The delta H for this reaction here is 177.8 kilojoules. Delta S is 160.5 joules. At 25 degrees, why don't you calculate the delta G and see, is this reaction spontaneous? All right, so let's take a look. So again, the situation, obviously, we're given the delta H, we're given the delta S as well. So why reinvent the wheel? We could just use the formula, right, that has both of those in there. And that would be this guy right here. So obviously, we need to convert our temperature here into Kelvin. So that's a 298 Kelvin. And we can put our values in, and our delta G in this case would equal our 177.8. I am going to multiply mine by 1,000. And again, I'm doing that just to convert it into joules. So my delta S is in joules as well. So everything will kind of work out. Again, if you don't want to do that, you do have to do some type of conversion of one of them. So you might have to take obviously the joules into kilojoules on the back end there. We'll times it by we got there 160.5 joules. So doing all that there, that's gonna get us looks like 129,971 joules, or we could clean it up to about 130 kilojoules, which kilojoules is typically what delta G is given in. First off, any questions on the calculation there? This delta G is a positive value, which tells us at 25 degrees, we would not expect this reaction to be spontaneous. So this reaction is non-spontaneous at 25 degrees. By the way, we would know that because what we just talked about, we had a positive value for H, a positive value for S, and the only way for this reaction to become spontaneous is a large temperature, right, or a high temperature, so that the back end of this formula will overtake the front end. Could we actually figure out when this reaction would become spontaneous? And the answer is we could use actually the same formula to figure out when this reaction might become spontaneous. And we could do that because we could set delta G equal to 0, because we know delta G needs to be negative, which is on the other side of 0, and delta H minus T delta S. And if I rearrange this and solve, that'll give me T delta S is equal to delta H. Obviously, here we're going to divide the delta S to the other side. And that'll give me the temperature is equal to the delta H divided by the delta S. Once again, here you still have unit issues, so you got to make sure you get into the same units. I'm going to again multiply my delta H by 1,000, and that's going to put everybody into joules. And if I do that there, we got 177.8 times 1,000 divided by 160.5. That's going to give me 1,108 Kelvin. We'll just call it a little bit of rounding there. And if I subtract 273 from it, that will turn it back into degrees Celsius, which is 835 degrees Celsius. 835 degrees Celsius would represent the minimum temperature at which this reaction would become spontaneous. I would say 835 degrees Celsius qualifies as a high temperature, right, versus 25 degrees Celsius in this case. And that's also what we see here in the graph. This is a graph of the equilibrium pressure of CO2. CO2 is a product here, and the only way we could get pressure associated with it is if we produce product. And you can see we do get to 835 degrees Celsius, and that's where our graph kind of comes out and starts to rise. It actually starts rising a little bit before that, but it actually doesn't reach standard pressure, which is 1 atmosphere, until about 835 degrees Celsius in this case. So that equation that we use, you could use it to calculate delta G and is it reaction going to be spontaneous. You could also use it in a case like this to figure out if it's not spontaneous, what temperature it would become spontaneous at. Any questions on that there? Yeah. All right, so why don't you give this one a go for the following reaction. Delta H is minus 1204. Delta S is minus 216.4. At 25 degrees, are the reactants or products favored? And calculate the delta G. Got our delta G equals delta H minus T delta S. Once again here, well, 273, 298 Kelvin. We're going to put our values in. Again, I'm going to do what I did previously, which is multiply this guy by 1,000, turning it into joules. minus our T, which is 298 Kelvin, and our S minus 216.4 there. And if we do that, pop that into the calculator. Looks like we end up with negative 1139512.8 joules divided by 1,000. Bring it back to kilojoules. Call it like negative 1140 kilojoules in this case. Negative means that this reaction is spontaneous, which means the way it is written, it should be heading towards the product sides are favored, as the reaction is spontaneously favoring to go from reactants to products in this case. Also, what we would expect to happen in this situation, as we had a negative value here and a negative value here, that turns this guy into a positive, and at low temperatures, the front number will always be bigger and give us a negative value there for delta G. Any questions on that one there? All right, the next thing we're going to talk about is phase transitions. And when we do a transition of phase, there is, as we talked about, some energy required to do that. And there's also an entropy change that occurs as you do a phase change. Remember that as we go from, say, solid to liquid, or liquid back to solid, that is the delta H of fusion, and that is the heat that's required to do nothing more than change that substance from solid to liquid and liquid to solid, not the temperature. Yeah. Where's that? Oh, that's actually Kelvin. Is the K? I think the K got uncapitalized there. So, yeah, that's actually Kelvin. Yeah, it's Kelvin times moles. Yeah. So sometimes the units don't perfectly kind of cancel out on these things. So I'm okay in the end on these if you kind of leave it as either like joules, kilojoules, something like that. But yeah, there's a temperature value associated with the entropy values and stuff like that. Typically, the delta H's and delta G's have more just kilojoules per mole, and this one is joules per Kelvin per mole. All right. So as we talked about, that heat of fusion is that energy, excuse me, required to do that transition. And for water, that occurs at 0 degrees Celsius. And the value there is 6.02 kilojoules per mole. And that is a delta H of fusion for water. We also have a transition that we talked about that goes liquid to gas, or gas back to liquid, and that is the heat of vaporization. And that's the same idea. That is the energy required to do those transitions. And for water, that occurs at its normal boiling point of 100 degrees Celsius. And again, remember, we're not changing temperature at these points. We're just simply changing the phase. And really at exactly 0 degrees Celsius, or exactly 100 degrees Celsius in the example of water, you do have both phases in equilibrium with each other. So for example, you have like ice crystals happening there at 0 degrees Celsius. At 100 degrees Celsius, you have some steam, you have some liquid water sort of happening. So they're in equilibrium with each other. And roughly the delta H of vaporization is about 40.6 kilojoules per mole in this case. And remember that it is the sort of same number for the delta H, regardless of which way you're going, but the sign changes. So if we're going from solid to liquid, that's going to be, in this case, a positive 6.02 kilojoules. And if we're going from liquid to solid, we need to release that energy, and it would be a negative 6.02 kilojoules. As we talked about, a positive value for energy typically is an endothermic type of situation. Negative value is more of an exothermic. And the same thing for our heat of vaporization. It's a positive 40.6 going from liquid to gas, and negative 40.6 going from gas back to liquid. So if we are doing this transition here, which is liquid to gas, that's going to occur at 100 degrees Celsius. And that is when we add 273 to it, where we get our 373 Kelvin from, which is our normal boiling point here of water. And because it's at equilibrium, our delta G in this case will equal 0, right? So at equilibrium, delta G will equal 0. And we get our delta H's here, and we could actually rearrange this and solve for our delta S in this case, bringing this to the other side and then dividing back gives us the delta S is equal to delta H divided by the temperature here. Temperature obviously would be in Kelvin. In this case, this would be the delta S of vaporization as we're going from liquid to gas. And that is basically our delta H of vaporization divided by our temperature there in Kelvin. And it gives us 109 joules per Kelvin here. And that is going to be our entropy of vaporization. And it is a positive number for our delta S of vaporization in this case. And that does make sense because we are going from liquid, right, to gas, gas being a more disordered state. And we would expect our delta S to be a positive value in that case. Now, if we were going in the opposite direction, really kind of doing condensation, which would be sort of in this direction, right? The only thing that changes in this case really is this guy would then become negative. And the result of that is if you do that, your delta S of vaporization, or really in this case condensation, I'll write it that way, is going to be negative 109 joules per Kelvin. And that would also make sense because if we're going from gas to liquid, we're creating more order and we would expect a delta S there to then become negative. So you could do this in both directions. You really value-wise, you'll get the same answer. The only difference there will be the sign to indicate, kind of, is it kind of gaining or losing order or disorder in that case. Any questions on that there? More importantly, though, when you do this and you rearrange this equation to get to this equation may also look very familiar to you because it looks very much like the delta S of the surroundings, which is negative delta H over T. The difference here is in the delta S of the surroundings, you need the negative. Here, when you rearrange it, there is no negative. And oftentimes people want to put the negative into this equation because they remember the other one. So if you're doing the delta S of surroundings, that one should have the negative. If you're kind of doing something like this, like a phase change, where you're kind of rearranging this equation, you should not end up with a negative. And again, people always want to kind of put it in there. Yeah. Yeah, so this is so usually you'll be asked, for example, you calculate something like the entropy of vaporization, could be worded entropy of condensation if you're kind of going that other way. You could also do something like the entropy of fusion, which again is the solid to liquid sort of transition as well. So this would only be done really at phase changes, which is an equilibrium sort of process, and that's where it's going to turn that delta G into a 0 and allow you to sort of calculate at that point. Also important that if you are not dealing with water, you will have different values for the heat of vaporization, the heat of fusion, and you will also have different melting point temperatures and boiling point temperatures if it's not water. So 100 degrees, for example, is not always the case if you're doing somebody else that may have a different boiling point. So that's something you want to keep in mind as well. Other questions on that there? So we try one here for mercury. 58.5 is the enthalpy of vaporization. What is the entropy of vaporization? Okay, so again, in this situation, we are doing a phase change. So that's going to give us our delta G, delta H minus T delta S. Here, that's going to equal 0. And that'll get us to rearrange this equation. T delta S is equal to delta H, dividing that to the other side will give us delta S of vaporization is our delta H divided by RT. Again, here for mercury, we see we do have different values, obviously, for delta H's of vaporization and also our temperature. So that would be 58.5. I'm times it by 1,000 to convert it to joules, since delta S is typically given in joules, and our 630 Kelvin is already in Kelvin, so that's good. So that's going to give us 58.5 times 1,000 divided by 630. And that looks like we will end up with a 92.9 joules in this case. Again, we're assuming in this case we are going from liquid to gas, basically. And that again is a more disorder situation, and we should expect our delta S in this case again to be a positive number, which it is. Once again, if we were doing more of the condensation version of this, which obviously is gas back to liquid, again, the sign on the top here changes, changing that to a negative, which again would make sense in that sort of opposite direction. Any questions on that there? All right, then let's talk a little about Gibbs free energy and equilibrium, because it's been a bit since we've done equilibrium, so we got to talk a little bit about it, I suppose. So here we got a couple more delta G sort of formulas. We got delta G is equal to delta G naught plus RT natural log of Q. So these are a couple different things here. This delta G is delta G basically under non-standard conditions. And a reminder of what sort of makes something standard conditions is basically if you're dealing with solutions, molarities need to be 1 molar. If you're dealing with pressures, they need to be 1 atmosphere. So that's sort of standard conditions. Again, 25 degrees Celsius. It's not technically standard conditions, but that's sometimes also a value that is used. This delta G is under standard conditions. So this would be our delta G naught that you would get by going to the table, for example, and doing delta G of the products minus delta G of the reactants. So kind of under those standard conditions, those table type conditions, that would be how you would get it. This R is obviously here our gas constant, and it is the one with joules in it, and it's the energy version of it, so not the one used for the ideal gas law. So that's the 8.314 version. T is our temperature in Kelvin. And lastly, natural log of Q. Q is our reaction quotient. Again, Q is calculated the same way as K, which again is our products divided by our reactants. So you do calculate it basically the exact same way. So you would obviously want to use this equation here if you have some type of condition that is not standard conditions. So not everybody's molarity is 1, not everybody's pressure is 1 atmosphere. that would be the situation where you'd want to use, obviously, the top equation here. Now, if we are at equilibrium, what happens to the top equation is our delta G there becomes 0, and our Q becomes K, and we end up with 0 equals delta G naught plus RT natural log of Q. Bringing this whole entire thing to the other side gets us our delta G naught is equal to negative RT natural log of K. So this one does have a negative in it. And the other thing that people will always want to do as well on the top one is they want to subtract rather than add. So people always want to kind of subtract that one rather than add it. So the R there is the gas constant from above, 8.314. The temperature, obviously, is the temperature in Kelvin, and K is the equilibrium constant. So when should you use that one? Well, I would recommend probably when it has something to do with equilibrium constant. Either you're given an equilibrium constant, you're asked to solve for an equilibrium constant, you would want to use the guy on the bottom there. So if you think about it, we've now seen 4 different sort of formulas, if you will, that involves G. We have our G like normal, products minus reactants. We have our G is equal to H minus T delta S. We have our delta G is equal to delta G naught plus RT natural log of Q. And we have our delta G that involves the K value there minus RT natural log of K. So as I said maybe the other day, the best piece of advice is based on the question, the information given to you, I would choose the G equation that kind of fits the information given to you is probably the best approach. Again, if you're given an H and an S, you don't need to go calculate it yourself and all that kind of stuff. So, you just go into that formula. Any questions on that? That also does bring up, by the way, with the R value in here, another very common situation that people screw up on, which again is unit wise. This is in joules. Again, this is typically in kilojoules. So you got that kilojoules, joules difference that you got to be careful of when you're doing the calculation. So again, that you're not off by that factor of 1,000. Any questions on that there? Now, when we look at this equation that involves the equilibrium constant, we can make some predictions, much like we have done before. And the good news about this is it involves the equilibrium constant, which means hopefully you understand what the equilibrium constant means at this point, and you can make your prediction, which means if we have a large value of K, that would mean that we would predict at equilibrium to have products. And the only way to have products would be that reaction would most likely has to be spontaneous to head towards the products. So those things should agree with each other. If you have a large value of K, you probably should have a negative delta G because that all kind of goes together. Opposite is true. If we have a small value of K, that means that we should mainly have reactants at equilibrium. And if we mainly have reactants at equilibrium, the reaction is really not going to the product side. It's going to be probably non-spontaneous and hang out at the reactant side. And you should have a positive value for G. So those things, again, should kind of agree with each other. If K is equal to 1, delta G will equal 0 because you're at equilibrium. All right, so why don't you give it a go here. Calculate the equilibrium constant for the following reaction. This is delta G value there, and the delta G for O2 is 0 kilojoules. Obviously, has something to do with the equilibrium constant, so that's definitely the sort of delta G equation we want to use. Delta G is minus RT natural log of K. In this case, we could get our delta G by going to the table and doing products minus reactants. And in this case, our delta G would equal 3 times 0 kilojoules for our products minus 2 times our reactants, 163.4 kilojoules in this case. And that is going to get us here a delta G of something. Come back, there it is. Looks like 2 times 163.4. Looks like negative 326.8 kilojoules. At this point, we know that this reaction is spontaneous, right? Because we have a negative delta G. We then can put it into our equation here. Our temperature is 25, so we'll do a 273 add-on to that there, 298 Kelvin, and we'll put it in. We'll go minus 326.8. I am going to multiply mine by 1,000 to convert it into joules. The reason I'm doing that is for this guy right here, which is R, which is in joules. So once again, you do have to do some type of conversion or you will be off. We can go 298 and natural log of K. We're going to take all this and divide it to the other side. And if we do that there, we've got negative 326.8 times 1,000 divided by negative 8.314 and 298. Gonna get us here 131.9 equals the natural log of K. To get rid of the natural log on both sides, that's going to do an E on both sides, right? That gets rid of that. And if we do that, looks like perhaps we get something like a equilibrium constant of 1.9 times 10 to the 57 in this case. Any questions on that calculation there? So we do see things that do agree with each other. Delta G being negative means the reaction is spontaneous. That should mean that the products we should be heading towards the products in this reaction. And because of that, we should probably have more products than reactants. And that should yield us a large value of K. So once again, these two things should agree with each other. Any questions on that there? All right, we'll lay it up there for today, I think.